Okay, class, we got a pretty difficult subject to discuss here. Neural integration. Now, it's real difficult because we're not doing face-to-face where I can answer questions directly and so forth. So you got to hang on everything I'm saying because it takes several facts to know already to understand this integration. Several facts to know already. I'm going to try to put this together in a capsulated fashion as much as I can here. All right. The first thing before we go to it, let's review EPSP and IPSP. Let's review that. All right. An excitatory postsynaptic potential occurs in neuronal transmission. First of all, neuronal, not neuromuscular, neuronal. An excitatory postsynaptic potential is when a presynaptic neuron tries to turn on a postsynaptic neuron. A presynaptic neuron before the synapse tries to turn on a postsynaptic neuron. What it's attempting to do is make this second neuron reach threshold. To make this second neuron reach threshold. Remember, threshold is a positive thing. Here's threshold. The EPSP and IPSP are not action potentials. They are graded potential. They are caused by ligand gates. Ligand gates. Go back to my electrophys. You're going to put all this together. So the neurotransmitter substance coming across then would open up channels to what? To sodium or sodium and potassium. Now, if they open it up just to sodium, it's much easier because sodium would rush in and it's positive to do this. If they open up to simultaneous sodium and potassium, it's a little harder because sodium would rush in and potassium would rush out. But remember, sodium has two reasons to want to rush in. First of all, it's positive and the inside of the cell close to the membrane is negative, and the concentration difference between sodium on the outside to inside is tremendous compared to the concentration of potassium on the inside versus outside. Plus, potassium is positive and the inside is negative. So far more sodium rushes in than potassium out. Okay? So you try to make it reach threshold. Okay. Now, this is happening though at one synapse on this here. And this and in a neuron, let me go back, in a neuron, the voltage gates don't start until the axon hillock. The synapses are back here at the dendrites and cell bodies usually. The synapses are back here and they're using graded potentials. You have to get enough voltage here through these graded potentials to make the axon hillock voltage dependent gates reach threshold. So it's kind of like a vote. You're voting back here and the cell body, and hopefully the vote is enough to give you enough stimulus to reach threshold here. But the voting is back here. Okay, now first let's go back. So an EPSP tries to make you reach threshold. Let's go to the next one. An IPSP is a vote to make you go further from threshold. So what will happen is it will either, the chemical neurotransmitter, whatever it is, will open either potassium channels. Potassium would then rush out, making the inside more negative, or chloride. Remember, chloride's higher on the outside, so it would rush in again, making it. So an IPSP is a vote. So if this is the guy that's receiving the votes to make him reach threshold, then EPSPs are trying to make him go yes, and IPSPs are making him not fire. EPSP votes are trying to make him reach threshold and fire, and IPSPs are making him not. Okay, so that's a review of that particular aspect there. All right. So now what we do, we go further here. And now what we do is basically this. We now go to looking at, that I want to point out, that any one neuron has multiple synapses to it. Now that's the next thing you have to keep in mind. Any neuron has many votors coming in, many synapses. You see how these synapses are all here? Many have many synapses. See, this is one dendrite here showing many even on one dendrite branches, not to mention on the multitude. So there's a lot of voting to any one neuron. Okay? So in order to turn this on, you have to summate up these votes. I'll say it again. In order to turn this on, you have to summate up these votes, no different than an election, and see if you have enough voltage by the time you get to the axon hillock to make it fire off. Now, there are two methods used: temporal summation and spatial summation. Temporal summation and spatial, and in most cases, it's really a combination. But we're going to separate the two out for academic reasons. Separate the two out for academic reasons. All right. So I'm going to start first. So we go back here where we were. So where we were integration again, and temporal summation and spatial summation. Temporal summation and spatial. So we started with, okay, see, and it involves the EPSPs and IPSPs, as I said. All right, so two, temporal summation and spatial. So I'm going to try to explain this as best I can. All right. If I go to, we're going to start first by going to temporal summation. All right. The key to temporal summation is to understand this: the fact that action potentials start to finish are a little over a millisecond total, whereas an EPSP and IPSP are several milliseconds. So let's see if I can find that. All right. Here's an action potential. Look, it's a little over 1 millisecond. Okay. A little over 1 millisecond, not including the hyperpolarization time, but a little over. So let's say that at the max, really, if I go, I'm looking at about 3 milliseconds. I'm looking at about 3 milliseconds, really, for the max. And that's including all these refractory periods and everything. So I'm saying about a 3 milliseconds. So I'll even go back and let's say that a little over 3 milliseconds. Let's say 3 in this case here. Some are much faster, depending on, but let's say a little over, looking at this particular drawing here, okay? Now, if I come back then and I look at this, though, the key to this really was this, that an EPSP, that's 10, that's 20, see, that's about 10 milliseconds. That's a lot different than that 3 millisecond or less. And the reason I like to use the 1 millisecond, because technically, remember, you could do another action potential during the relative refractory period, and that's just 1 millisecond. So you can actually make action potentials get close to 1. That's why I use the 1 millisecond to show that particular activity there. But if I just took the whole thing, then yeah, it would be around 3 or something like that there. But you can do another one in that relative. Remember my electrophias. But anyway, let's go back. So other words, an EPSP is 10. That means you could get theoretically about 10 action, at least not 8 action potentials if you take the relative refractory period before one EPSP had finished. Before one EPSP, and remember what the EPSP is doing, sending in that sodium stuff. So if I did, now think about it, if I did one EPSP and got some sodium, but came back real quick and did a second one, and then came back real quick and you wouldn't have leaked all the first out before I've accumulated some more sodium. You see, by the fact the action potentials that are coming to this neuron. So action potentials are coming to this neuron. Let's say action potentials are causing graded potentials here, because the action potentials would be coming from here. We come here, Action potentials would be coming. Then you'd cause a graded potential. Another action potential. More sodium's building up. Another action potential. And you're doing all these action potentials from this presynaptic before, and each one is bringing in more and more sodium. So it's accumulating. It's accumulating. It's accumulating. So what would end up happening is, and that's true even for the IPSP, look, it's about the same time frame. So what would essentially happen is, because we'll go back, that action potentials can come in as really close as 1 millisecond, that you could build up electrolytes in there that might have enough to influence this neuron to fire at the axon hillock. Now, the only thing I'm going to say is, no matter how fast one fires, it is absolutely true that a single EPSP cannot. That means that even if you only had this coming in, this one, and all the others not firing, he still would not have enough, no matter how fast he fires, to make this neuron reach threshold. So you still are going to have several firing at the same time. But you could have just a few firing. Of all of these you got now, just a few firing so fast that the accumulation of sodium would be enough, that there would be enough sodium to slide down this neuron and finally make the membrane reach threshold here. So it's a time thing. Fast firing, temporal summation, time summation. That's temporal summation. Okay? Now, on spatial summation involves the fact that all the neurons have several synapses going to, thus the graded potentials are added up in space. That's what we're seeing here. So let's do this very quickly. Okay? So that's spatial. Assume the axon hillock, as I mentioned, performs algebraic summation. Assume to start action potentials in the axon hillock, first area to have voltage dependent gates, must get up 30 millivolt charge for threshold. Okay? Must get a 30 mil. The dendrites and cell body do graded potentials. Okay. Let's say that the resting membrane potential at the axon hillock is a negative 70. To reach threshold, then we need a plus 30 charge. So the membrane needs to get a 40 millivolt at the axon hillock to fire action potentials. There are several synapses on the dendrites sending EPSP signals. All these signals give us a plus 40. I'm adding all the EPSPs up. Okay? Hit at the axon hillock. But we have several synapses sending IPSPs, and they give us a negative 40. Thus, at the axon hillock, we still at a negative 70 millivolts, because plus 40 neutralized the negative 40. Okay, let's go to the next one. Another scenario. There's several synapses on the end sending EPSP. All the signals give us a plus 40 hit at the axon, but we have several synapses doing IPSPs. Okay? And they give us a negative 20 at the hillock. So the membrane potential at the hillock now is a plus 20, plus 40 minus 20, bringing the axon hillock to, let's say, a minus 50. But we needed a minus 40 because we needed a 30 to reach threshold. So we're closer there, but not there. That's what we call facilitation. Closer to threshold, but not there. Okay? Go to the third one. There's several synapses on the dendrites sending EPSPs. All these signals add up to a plus 40. But we have several sending IPS that give us a negative 10. Now we're at a plus 30. See what I'm saying? We had a plus 30. Now we're at a negative 40. So we've reached threshold and we start action potentials. The last scenario, so see that third one, we reached it. But we added up in space, spatial summation, all of them firing. Fourth, several sending, all give us a plus 40, but our IPSPs measure a negative 50. So see now we're negative 80, we're further from threshold, so we're inhibited. I want you to read on this, but this gives you kind of an idea how that integration occurs. Thank you.